I welcome you all in this course on steam and gas power systems. Today we will discuss about the compounding of steam turbines. Compounding of steam turbines basically means, or the objective of the compounding of steam turbines is to have the same output with reduced RPM, because single stage steam turbine gives very high RPM. So, in compounding, the basic objective of the compounding is, without altering the output of the turbine, the RPM of the turbine is reduced so that it can be used for power generation. Now, before we go for the compounding, we will discuss about the D level turbine first, and then we will go for pressure compounded steam impulse turbine, velocity compounded impulse turbine, impulse reaction turbine, and then we will discuss difference between impulse and reaction turbines. So, first of all, we will discuss the single stage D level turbine. D level turbine. This is a single stage turbine. So, there is a shaft in this turbine, okay, and on this shaft the blades are fixed. So, there is only one row of the blades. So, it is going to be like this, and this appears to be rectangle, but it is a curved plate or a curved blade like this, So, when we take the elevation of this, it will appear to be a flat plate, right? And proceeding through the blade, there is a nozzle. Normally, it is a converging diverging nozzle. Now, this nozzle sends steam to the blade. So, this is a nozzle, converging diverging nozzle, right? And let us house this, and this is exhaust. And from this side also it is closed. This side also it is closed. Okay. So, now this is converging diverging nozzle. As we know, in a converging diverging nozzle, the velocity of steam coming out of the converging diverging nozzle is quite large, and normally it exceeds 1000 meter per second, let us say, and normally in D level type of turbine it is 1100 meters per second, right? And this steam glides over the blade, okay, and blade is, if the shaft is along the board, then the blade is like this, and when it glides over the blade, it exerts force on the blade, and the blade, a tangential force is exerted on the shaft with the result and rotational motion, because there are number of blades, okay, there is series of blades circumferentially and axially. But this is a single stage turbine, so there is only one row of blades, okay, circumferentially there are number of blades, but axially there is only one row of blade in D level turbine. And if you look at the variation of velocity and pressure in this turbine, let us make this half shaft, pressure and velocity variation. We'll draw, this is nozzle, blades, and there is a recess between nozzles and the blades. This is the line. So this is the line, this is the line, this is the gap for nozzle and this is for blade, right. So if you look at the variation of pressure, so there is a variation in the pressure in the nozzle right from the entry to the exit, from entry to exit there is a pressure drop in the nozzle. In RESs we do not consider any pressure or velocity loss, so it goes on like this. And what about this pressure loss in the impulse turbine blade, because pressure loss in the impulse turbine blade is 0, there is no pressure drop in impulse turbine blade, so it is also going to be straight. And this is going to be the condenser pressure. This pressure is condenser pressure. Now regarding the velocity inside the turbine, the velocity also here increases, it increases in nozzle, velocity of steam, because nozzles are basically used to convert pressure energy into the kinetic energy. So velocity increases in the gap between the blade, because there is small gap between the nozzle and the blades, so it remains constant here, and in the blades the velocity keeps on reducing, and here exhaust take place. This is almost this is V2, and in fact a lot of energy is going out with this velocity of steam. It is approximately 10 to 12%. That is the kinetic energy which is going out of this steam first of all. So this is the wastage of energy. So it should be trapped in order to improve the efficiency of the turbine. Its inlet velocity is approximately 1100, I stated earlier also, meter per second. The velocity U, the rotational velocity of a rotor, is approximately 3500 meters per second, and N RPM is 3000 RPM, 30,000, right. So in D-level turbine, single stage turbine, the RPM is 30,000. RPM is 30,000. Inlet velocity is 1100 meters per second, and approximately 10 to 12% of the kinetic energy is going up with the exhaust. So these are the main drawbacks of this single stage D-level turbine. Now in order to improve the working of this turbine, first of all we have to reduce the RPM, we have to reduce them to an acceptable value. Second thing is, this losses due to this kinetic energy of steam which is leaving the turbine have to be minimized. Okay. So for this purpose compounding of turbine is done. So this turbine is used for the smaller power generation, but through compounding we can reduce the RPM and we can reduce these losses also. So for the purpose of compounding, we will draw another diagram, and this compounded impulse turbine is also known as Retio turbine. In this turbine, the pressure drop does not take place in a single nozzle. So there are a set of the combination of blades and the nozzles. So one stage consists of one set of nozzles and blades, right. So D-level turbine was a single stage turbine. So in Retio turbine there are number of stages. If we depict them pictorially, the turbine is going to be like this. There is a shaft. On the shaft there are blades. First of all we will depict the blades. There are blades. Right, and there are nozzles. And here also there are nozzles, there is another nozzle. Similarly, we can have n number of stages. I mean, each stage will consist of a set of nozzles. there can be n number of nozzles circumferentially, but actually there is only one grid. There is only one grid of nozzles and one grid of turbine blades, right? Similarly, we can have number of stages, right? When the pressure is reduced, the volume is increased, so the size of the turbine is also increased. We can have n number of stages here also, right? Now these nozzles, these blades are fixed to the shaft and they rotate along with the shaft, but nozzles, they do not rotate along with the shafts. In fact, there is a small gap between this and between the nozzle body and the shaft, and at the top they are fixed with the casing. So they remain stationary, only the blades, the blades which are fixed on the shaft, they rotate with the shaft. Now here, if we draw again, if we draw projections from the nozzles, these are the projections from nozzles, this one, then from the blade, this one and this one, then again from the nozzle, then again from the blade, and so on, right? Now in the nozzle, let us start with the pressure drop. So pressure drop in the nozzle is going to be like this. It is not linear, but because the distance is small, it appears to be linear, but it is not linear. Then in the races, it remains constant, because in races we assume that there is no, this gap is very small, it's much smaller than which is appearing here, so it remains constant. And now in the blade itself, there is no change in the pressure because it is an impulse turbine. After the blade there is a recess, there is no change in pressure. Then again there is a nozzle, there is a pressure drop, and then again pressure remains constant. So what happens here? The pressure, entire pressure drop does not take place in a single nozzle. It is being splitted in number of stages. Since the pressure drop is being splitted in number of stages, the steam entering the first stage of the blade will not be, the velocity of this steam will not be very high, like 1100 meters per second. So it is going to be low because pressure drop is low, right? And what about the velocity? Now we'll start with the velocity. In the first set of nozzles, the velocity will increase because there is a drop in pressure, velocity will rise. In races, the velocity will remain constant, right? And then in the blades, the velocity will fall, okay? And then again, it will remain constant in the recess space, then again in the nozzle it will rise, right, remain constant, and then it will fall. So velocity will keep on rising and falling. Pressure is simply splitted in number of stages. The net effect is the RPM of the turbine is reduced. Output is same, but the RPM of the turbine is used, and this turbine becomes more useful for power generation. And when we talk about the carryover losses means losses or the kinetic energy being taken away by the steam which is leaving the turbine. These losses are only 1 to 2%, very less in comparison to the D level turbine. So this is the pressure compounding of turbine. Pressure compounding means pressure drop does not take place in single stage, but it is splitted in number of stages. Now another is velocity compounded turbine. The velocity compounded turbine is the Curtis turbine. Okay, so Curtis turbine is a velocity compounded turbine. In this turbine, the velocity is splitted, pressure is not splitted. In pressure compounding turbine, the pressure is splitted. So in a velocity compounded turbine, there is only one nozzle, the shaft. On the shaft, there is only one nozzle. Let me make it bigger, otherwise it will create confusion. There is a shaft and there is only one nozzle, right? and this will keep, this is a diverging passage because the specific volume of steam is increasing. So, it is a diverging passage, and in this diverging passage we have blades fixed on the rotor. So, there are blades and there are blades to give they are fixed blades. There are two types of blades here, moving blades and fixed blades. So, moving blades are in contact with the rotor or are fixed with the rotor, and fixed blades are fixed in the housing. So, there is another fixed blade. Now, I will tell you the purpose of having moving blades and fixed blades, right. So, and then there are again, we will draw the projections from here, nozzles, and then fixed blade, sorry, moving blade, fixed blade, moving blade, fixed blade. So, there is only one nozzle here, and in this nozzle, as in case of other nozzles, there is a pressure drop and there is a rise in velocity of the steam. Pressure drop takes place only in this stage, only in Curtis turbine. In remaining stages, there is no pressure drop. So, pressure remains constant after the pressure drop, the pressure remains constant, or we can swap them for the sake of convenience. So, this is pressure drop and pressure drop remains same, then the pressure remains same in remaining stages in Curtis turbine. And regarding the velocity, first there is a rise in velocity because the purpose of the nozzle is to increase the velocity, then there is a recess. So, in the recess the velocity remains constant, here there is a drop in the velocity, guide blades there is no change in the velocity, and then again there is a drop in the velocity, then guide vanes there is no drop in the velocity. So, in velocity compounded turbine we can have another blade here. So, then again there is going to be a drop in the velocity. So, in the velocity compounded turbine the entire velocity is splitted into several stages, that is why it is known as velocity compounded turbine. And the previous turbine which was Ratu turbine, in Ratu turbine the pressure was splitted into the number of stages, okay. And after this we will take up velocity and pressure. So, we can have combination also, we can have a combination of velocity compounding and pressure compounding. Certain stages are velocity compounded, then again certain stages are velocity compounded, and in between there is a pressure drop. So, we can have similarly, we can have another nozzle here, for example, another nozzle, then velocity compounding, then another nozzle velocity compounding. That type of arrangement is known as pressure and velocity compounding of impulse turbine. Second type of turbine is impulse reaction turbine. In impulse reaction turbine, the output is generated not only by the impulse of the movement of the impulse in the movement of the steam or rate of change of momentum of the steam, but also by expansion of steam or pressure drop of steam in the blade passage. Pressure drop of steam in, so blade passage is not uniform, okay. So, expansion of or pressure drop of steam also takes place in the blade passage, and the power is generated. And for impulse reaction turbine again, and the blades are, there are two types of blades, profile type of blades and aerofoil. So, this impulse reaction turbines, they have aerofoil type of blades. We will discuss them in details in subsequent lectures. We will discuss this impulse reaction turbine in details, but the shape of the blades in impulse this reaction turbine is aerofoil type, and there is a change in the cross section area of the passage, and that is how the reaction is created in impulse reaction turbine. So, this turbine is also having stationary blades and moving blades, stationary blades and moving blades. Since pressure drop takes place in both the cases, stationary blades as also and the moving plates also. And there is a special type of turbine which is known as Parson turbine. In Parson turbine 50% enthalpy drop takes place in stationary blades, 50% enthalpy drop takes place in moving blades. So, suppose there are 10 stages. So, in each stage it is 50% in moving and 50% in stationary blades, right. So, this is how I mean reaction turbines are compounded, because they do not have nozzles, they have only passages. One grid is for stationary, another is for moving. Pressure drop takes place in both the stages, right. So, we will discuss this impulse reaction turbines in subsequent lectures. Now, difference between impulse and reaction turbines. Now, difference between impulse and reaction turbines, difference. In impulse turbine, pressure drop is in nozzle only. Impulse reaction turbines, they do not have any nozzle, and pressure drop takes place in the entire length of the turbine or along the axis of the turbine rotor. In impulse turbine, there is a constant blade channel. So, blade channel. So, there is no pressure drop in impulse turbine. In reaction turbines, there is a variation in the cross section in the blade channel, that is why there is a pressure drop in a reaction turbine. Third is, they are profile type of blades in impulse turbine, and in reaction turbine they are aerofoil type of blades, and this causes pressure drop in the channels in impulse reaction turbine. Fourth one is, in impulse turbine we can have partial admission in the turbine. For example, there is a side view, suppose there is a side view of the turbine. So, we can have nozzles at different locations. So, we can activate only these nozzles. We may not supply steam to this nozzle. So, partial admission for the sake of controlling the output of the turbine is possible in impulse turbine, but partial admission. But this is not possible in impulse reaction turbine, because in impulse reaction turbine we do not use nozzles, those nozzles are not being used. So, here there is a diaphragm consists the nozzles, a grid of nozzles, and we can partially supply steam to these nozzles, or we can select number of nozzles to which the steam can be supplied. So, this is possible in impulse turbine. Fourth is, power developed in impulse reaction turbine is more. So, power developed in impulse reaction turbine is higher than the impulse turbine, and this impulse turbine, if you look at the size of the turbine, so impulse turbines occupy less space if you compare with the impulse reaction turbine, but their efficiency is low. Efficiency of impulse turbine is less than the efficiency of an impulse reaction turbine, a bit less than the reaction turbine. And so, these impulse turbines are used for low power generation, but the benefit of these turbines is their blades are easy to manufacture, they are lighter in weight, and they causes less stress on the, because blades are fixed on the rotor, they are fixed on the rotor. So, if they are light in weight, easy to manufacture, they are light in weight, they are fixed on the rotor, and they cause comparatively lesser stress on the rotor. So, that is the benefit of impulse turbine if you compare with reaction turbine. Okay. In the next class, with the next lecture, we will start with the analysis of a power generation in impulse turbine.